All right, master students, welcome back to this continuing series on conformation analysis. Now, we want to look at uh, uh, chains, especially rings. There's some terminologies that I need to introduce first of all before we look at rings, which you want to look at from the three-membered ring, four-membered ring, and above. So there are some two terminologies that you'll encounter when you're dealing with the the way uh, the atoms are arranged. Uh, uh, the way the atoms are arranged in a chain. So there are some two terminologies. One is acyclic. It means that this is one in which there is no ring. It's just called an open chain system. Acyclic. That's the one. Acyclic. And the other one is cyclic. So you're going to see that the smallest type of chain which you can form is a three-membered ring. Yeah. So here I've listed the strainer. I'm just going to show you here. The good thing is that with this video series, you can be able to see the things that you are trying to illustrate using molecular models. What can you see here? Just take the black balls as carbon atoms, and then the others as different different what different atoms. In this case, I usually put in a standard manner the white ones as hydrogen, and then red as oxygen, and then probably blue can be nitrogen. So that's usually the standard way in which I put that. And then probably if you can see something like a small green, it may be something like a halogen, something like that, and it's got a single bond, something like that. Yeah. So those are the standard things in which you can see me showing here. But okay, so let's get back to our three-membered ring. What can you see? Yeah, it's quite a strange system. Um, what to do is this: is that if I'm to open it up, okay, let me just try to add an atom there. Now, now, in this case, this was an open system to which it contains uh, three carbon atoms. Can you see it's so relaxed? It being a single bond, there is there is free rotation. The bond angles in an open systems are 109.5 in that. If I was to remove one of the atoms here, this, okay, let me just try to show it here. This is it's a tetrahedral. Can you see that? It's a simple tetrahedral. And the tetrahedral, the bond angles are 109.5, provided there is no lone pair. Yeah, 109.5. So now I've now put it back to the ring there, and then what I'm going to do is that I want now to form a three-membered ring. Yeah. So you're going to see that I'm just going to remove this atom there, and then I want to see whether I can join here. This is something which you're going to be doing in the next part about cyclization. That there are some rules developed by a scientist called Baldwin. So you're going to see something called Baldwin rules on ring closure. But for now, let's just look at you've now formed what? Something like a ring. In this case, like a three-membered ring. You're going to see that if you're going to form a three-membered ring, can you see? You're going to be straining, you're going to be like bending. Can you see the way if I leave it, this is the relaxed? Can you see how I'm actually straining? Yeah. Yeah. So in fact they look like like they are bent. Yeah, like the bones are bent. So until I get to 60 degrees, oh yeah, can you see? Yeah. Good. So there is really a lot of strain in that bond. 60 degrees in a three-membered ring, it's really strained, really strained. Can you see how it looks? If it's going to be flat, some three bonds are top, the others are at the bottom. Yeah. Can you see how it is? How ring looks like when it's flat, when it's horizontal. Some atoms are at the top, some at the bottom. So this is a three-membered ring. So what I want to do, I want now to add, so in this case, we are seeing the ring strain, it being shown in kilocalories. You know, a calorie is, nowadays we use joules. So if figures are given in calories, how do you convert them to joules? One calorie is 4.184. Yeah, 4.184. 1 calorie is 4.184 joules. So you can multiply by this one times 4.184. So you see it's about 100 kilojoules per mole. That's a significant amount of energy. 100 kilojoules per mole. Almost 110, yeah? That is almost equivalent to what? To breaking a carbon-carbon bond, something like that. Yeah. So it's quite a significant amount of energy to try to have a three-membered ring. A four-membered ring slightly smaller than a three-membered ring. Let me just try to see whether I can introduce. So this is what I had as my three-membered ring. So I want to open it up. I want now to add an extra bond, and then probably I remove that, and then I form, can you see, there is strain, but not as large as the one for the three-membered ring. Yeah. So now the bond angles are 90 degrees. Can you see? For a four-membered ring, once again, the thing is, some atoms are at the top, some at the bottom. This is a four-membered ring. Can you see? That's a four-membered ring. Now, let me just try to extend the chain slightly more by adding. I want to add an extra carbon atom. Yeah, as it's like a CH2. It's like a homologous series. So I've added. Can you see? So by just adding to form a five-membered ring, this it's not much of a strain like it was for a three or a four-membered ring. Yeah. What can you see here? Yeah. So this is a five-membered ring. Can you see? Let me just try to move a little bit back. So you can see now the way uh, the atoms arranged are arranged around the five-membered ring. And then I want to introduce the extra atom to make excuse me, to make a six-membered ring. Yeah. So I've now added a six-membered ring. This is a six-membered ring. Can you see? 1, 2, 3, 4, 5, 6. Now, this may not be able to show very well, but a six-membered ring exists as a chair. So what I'm going to do is I want to get a different representation. This is the same as this. Okay, let me just try to show by adding okay, let me remove that, and then let me have here. So this is an open six-membered 1, 2, 3, 4, 5, 6. Can you see like this one as well? Yeah, these are different representation, and excuse me. Yeah. So for this one, it will be much easier to show. 1, 2, 3, 4, 5, 6. These are six-membered ring. So I want to see whether I can form a ring. Yeah. So I'm just going to remove those two, and then see whether I'm going to form a six-membered ring. Yeah. This is a six-membered ring. Now for this one, it will be very easy for me to show like this one. What can you see here? It's still a six-membered ring, but if I put it here, I can see something like a chair. Yeah, can you see? There are some atoms down and this one's up. So in other words, you're having this system looks like this one here. It looks like so that there is a hydrogen here, there's a hydrogen down, there's this hydrogen up, there's this other one here, and then this one is up here, there is down here, there is that, and then there is down here, here there is up, and then there is down, and then lastly there is top, and then there's that. Can you see that? That is a chair, yeah. And then there is the other conformation which is like the boat, yeah. Can you see? In this case, in the boat, these two hydrogens are a bit closer to each other. Now, if I'm going to have a chair, uh, there are some three atoms which are at the top, which are called the axial position, and these are the ones which are horizontal. They are called the equatorial position. Yeah. Now, a chair can there are two conformations of the chair in that this one can come up and this one can come down. That's still a chair, and then this one can come down and this one can come up. So that is still still a chair. Can you see that? Can you see that? Very well. So that is a chair. Now this is a boat, yeah. Top, and this is the top here. This a boat. Can you see? There's a top and the top here. But all in all, it's still a six-membered ring. 1, 2, 3, 4, 5, 6. Can you see what? Let me move behind. 1, 2, 3, 4, 5, 6. Still a six-membered ring. Okay. So this is a boat. This is a chair. Okay. But once again, when you'll be in session, you'll be able to hold these molecular models to be able to really show rather than just showing it on the video. But I think you can be able to get the point in which I'm talking about. So the six-membered ring has got no ring strain, and in nature, the six-membered ring are the largest, are the highest number of ring sizes you'll ever get. The one for the seven-member ring and the five, they have almost the same ring strain. And then 8, 9, and so the other ring sizes are going to have higher ring sizes, but in general, yeah, they at your level, you'll be dealing with between 3 and up to probably 8-membered ring, yeah. Yeah. Higher it will be when you'll be dealing with specialized courses, especially on heterocyclic chemistry. That's when you begin to look at bigger ring sizes. Yeah. So something I may need to mention is that, and I think before I really stop on that, is that if you're going to have a bulky group at the axial position, it's going to cause steric hindrance, especially if I'm going to put, let me put a second group. Uh, Let me put a second group at the axial position. All right. So this is what I have. I want to, okay, that is the, okay. So this is what I have as my, okay, let me put it correctly. Okay, good. So I want to put a second group at the axial position. So I've got two groups at the axial position, and you can see there's a lot of uh, knocking on one another. This is called steric hindrance. But the same ring system will be more relaxed in this other conformation in which the two bulky groups, they are occupying the equatorial position. Can you see here? So this group, even if it rotates, and this one, even if it rotates, they are further away from each other. Yeah. So the conformation in which the bulky groups are at equatorial position is the conformation with the highest population. So there will be very little, if any, percentage of the molecule existing in the axial position, because there will be a lot of steric hindrance. Okay. So I think that's the much I'll talk about. That's the bulky groups at the equatorial position. This the bulky groups at the axial position. Yeah. Okay. So I think uh, I'm going to stop there. Uh, the notes um I've told you to read, especially on this textbook on uh, uh, Paula Bruce. Yeah, you'll be able to look at the sections, chapter 3, I think from 3.11 to about 3.16, I think it's there. So there are sections dealing with conformation analysis on, especially on the ring system. So you'll be able to look at that. With this course, I'll be able to give you the 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 reference notes that you'll be able to look at to be able to understand more information than the information I'm giving you in this short video. So I really hope you've really enjoyed this section on the conformation analysis. The next topic I will be talking about shortly will be on Baldwin rules. They're just rules which are defining, assuming you've got an open chain whereby there is a there's a nucleophile on one and there is an electrophile, especially within the same chain. Yeah, there are ways in which you can have the nucleophile attacking the electrophile, and then there is a leaving group coming out, and then you're going to form a ring. So you're going to see there are some rules which show there is a cyclization which is going to be said to be favorable, and the other one which is not going to be favorable. And they're going to see the ones which are going to be favorable, dealing with the various ring sizes. Uh, and then um, uh, we'll also be looking at when you're dealing with carbon being tetrahedral, and one containing a double bond which is going to be uh, trigonal carbon, and then the one which is going to be containing a triple bond is going to be said to be digonal. Yeah, so there are those terminologies. Tetrahedral uh, for carbon containing 4 bonds. The one containing 3 bonds will be said to be trigonal, and the one containing a triple bond is going to be said to be digonal, in which the bond angles are 180 degrees. So there are those things I'm going to be mentioning later. So I hope you've really enjoyed this short video. Thank you very much. Okay.